Hello, my name is Javier Diez. I'm going to present a work made in collaboration with Alejandro González, like me, from the Instituto de Física Arroyo Seco, and also in collaboration with Kondic from the New Jersey Institute of Technology at New Jersey. The problem I'm going to talk about, it's about the phase separation and the wetting of nanometric films. These films are made of melted or liquefied metallic alloys which were previously deposited on solid substrates. This problem is of interest in application because it gives place to the formation of nanoparticles where the metals are separated, and this can be related with multifunctional properties. The experiments are made on silver and nickel, and the films are melted by the illumination with larger pulses of a duration of about 20 nanoseconds. The modeling is made by using gradient dynamics under lubrication approximation, and the challenge is to describe the simultaneous operation of two instabilities, like the wetting of the substrate and the phase separation in the alloy. So here are some pictures of the experiments which show that effectively there is simultaneous phase separation with the wetting of the film. These are pictures for 1 and 5 pulses for cases with 3 different thicknesses of the films. To give an idea of the dimensions involved in the problem, here we present a table of the grain size of this phase separation and the distance between these grain sizes of island, which are the spacings. Finally, after several pulses, what we have is a pattern of drops formed by separated metals, as shown by the colors in these scanning pictures. So from the modeling point of view, we start with the free energy functional, which include all the energies at play in the problem, which is the surface energy within the lubrication approximation, the field-substrate interaction through the van der Waals forces, the Gibbs energy of the problem, which depends on the concentration of each metal, and the energy due to the strong gradients that produced when you have separation of the metals. And the constants involved in this energy is what we call the interfacial stiffness. Here what we have is two variables, H and psi. Psi is the thickness average bulk concentration, and these two quantities are conserved and as shown here by integrating this variable over a given area of the substrate covered by the film. So by means of the variational principle, we can obtain the governing equation in a conservative form for H and psi, where we see that this evolution equation or dynamical equation are governed or driven by the gradient of pressure and the gradient of chemical potential, and that there is also a diffusion process within the mixture controlled by the molecular mobility of the problem, which is in fact proportional to the diffusivity of the alloy. The fluid-substrate interaction is described by main means of van der Waals forces in this form, in such a way that it includes both the repulsive and the attractive forces between the molecules in the mixture and the molecules in the substrates, and which has a given equilibrium thickness for the interaction. And the Gibbs energy in this case is described by a double wall potential in function of the concentration of one of the metal. In this case, phi refers to the concentration of the silver, And this is because we have to use this quadratic form because we don't have a small concentration, but concentration of the order of 0.5. In this equation, the pressure and chemical potential depends on H and psi according to these equations, where here we can distinguish the capillary pressure as the Laplacian of H, the disjoining pressure, and the osmotic pressure, which comes from the Gibbs energy, and the part of the pressure which comes from the energy through the interface between the phases separated. All these expressions include dimensional numbers, which depends on the stiffness, the surface stiffness, the Hamaker constant, the equilibrium thickness, as well as the temperatures. And these are parameters that have to be determined for these experiments. Some of the data are taken from the literature as shown here, and some dynamical parameters like raw density, viscosity, surface tension, and diffusivity are for the alloy are calculated by weighted average of the simple metals values taken from the literature, but these values are known also to depend on the temperature. Here the index M refers to the melting values at melting temperature, so we use this expression as a function of temperature, and the interfacial stiffness, which is a new parameter here in this description, can be calculated from the interfacial surface tension between the both separated phases, like silver and nickel, and this can be approximated by the well-known Hirifalco-Good formula, which depends on an adjustment constant Cm here, which we have to calculate also for this problem. So in order to be able to calculate these quantities, we develop first the linear stability analysis of the governing equation by perturbing to first order the conserved variables H and psi. And in this linear stability analysis, what we found is two modes. One we called H mode and phi mode. One accounts for the instability of the thickness, and the other accounts for the instability of the concentration. That means that if it's unstable, it leads to this separation of phases. And these modes, these eigenvalue problems, also have the eigenvalues, which are the dispersion relation named before, and they have also the eigenvalues, which shows that if one perturbs in one mode, one perturbs the thickness, one inevitably also perturbs the concentration, but there is another mode in which one can perturb the concentration even without perturbing the thickness, so that the film remains flat. Of course, from this linear stability analysis, since it is analytic, one can also have the expression for the maximum growth rates and the wavelengths and wave number at which these maximum growth rates produce, and these expressions will be very important to determine the characteristic constants of our experiment. In fact, from our experiments we can take, for instance, typical length values for the separation of the instability of the concentration, which we assume that they are lambda the wavelengths of maximum growth rate for the instability of the concentration, and the times that in the experiments in this instability are observed, with these values here plotted in this graph, which are this horizontal line. We are able to look for a given temperature at which we have these values from the linear stability expression, and then we can calculate which temperature corresponds to our problem, which is the value of the constant Cm. the values once that we have the temperature T and from the distances between drops for long times at the time of the evolution for the formation of these drops, one can also have for a given temperature from the expression of the linear instability, the values of the thickness of equilibrium, and also the value of the Hamaker constants, which are these black points here. So now we have all the parameters to describe the problems, and besides using the linear instability analysis, we can do also numerical simulation of the governing equations. And these numerical simulations, okay, here first, before the numerical simulation, I have here the growth rate of the instability, which has this curve which show the dispersion relations. But I was starting to talk about the numerical simulations, and these are numerical simulation along one direction x. And so we start with first with the film that we perturb, and along the time we try to observe what type of drops we get, and we see that by following the red and black lines that inside the drops contoured by blue, we have the separated metals because the concentration goes from 0 to 1. And we can also see a movie of this evolution to see how, starting from the thin film with some perturbation, we can obtain drops where the faces are separated inside them. Also, we can do 3D simulations by not only consider one coordinate x, but also x and y, and we see that after some time of the evolution of the film, we get the drops with the faces separated inside them, and we can see that in a picture how the instability develops. And we see that there is also qualities of drops once they have formed, and finally they get a final shape, as we show here, which are similar to the ones we observe in the experiments. So as a summary, I could say that we have shown experiments where there are simultaneous dewetting and phase separation nanometric films, and there are patterns of drops formed by drops which show separate with the metals of the alloy as alloy and and we were able to model this problem by using the gradient dynamics theory. By means of the linear instability analysis, we were able to calculate the parameters for the experiment and show similar forms of the drops and composition of the drops, either in 1 dimension and 2 dimensions. Thank you.